more like that. So today I want us to proceed to the last two separation techniques before we go into the second chapter, which is the mole concepts. So let's just continue with, I want you to bring out your notes and the writing material so that you can jot properly. So we stopped at simple crystallization last week. We said simple crystallization techniques is a separation technique that is used to obtain one pure solid for its solution. So the next one, which is number 10, that I'll be checking today is fractional crystallization. Fractional crystallization. So fractional crystallization is different from simple crystallization. And the major difference is that in fractional crystallization, we use it to separate two or more soluble solid based on the difference in solubility. So we have two soluble solids that has differences in their solubility level. So we use fractional crystallization to separate such substances. But if it is that we want to obtain one pure solid from a solution, when impurities are present, we cannot use fractional crystallization. We simply use the simple crystallization technique. So the difference between simple crystallization and fractional crystallization is that fractional crystallization gives us this upper edge to be able to separate soluble solid, either two or more, they can be five, but they must have differences in their solubility level. The solubility must not be the same thing. But if you want to obtain one pure solid from a solution, when there is impurity or when impurities are present, you can use simple crystallization. So let me just quickly give you the note. Fractional crystallization. I believe you get that easy. So when we talk about fractional crystallization, it's just a separation techniques that's used to separate two or more solids, two or more soluble solids based on difference in solubility. So the thing you need to take note that I told you about last week is the principle. Like what JAMB will ask you is they can ask you the principle that fractional crystallization used in separating two or more substances is difference in solubility. That is the principle. So fractional crystallization is used to separate two or more soluble solids based on the difference in solubility. For example, if we have sodium chloride, which is a salt, and potassium nitrate also, which is a base, if they're in a solution, both of them, they are soluble solids, but they have different solubility level. Potassium nitrate has higher solubility level compared to sodium chloride. So therefore, we can use fractional crystallization to separate this kind of mixture. So anytime you hear the word fractional crystallization, the first thing that should come to your mind is that you want to separate two substances that are very soluble, but they have different solubility rates. I believe that is taken. They must have different solubility and they must be soluble. The two of them must be soluble. So like I said, example is separating a mixture of sodium chloride and potassium nitrate from a solution. I believe that is taking place. Is that here? Is that here, please? I want your reply.
Yeah, yeah, but I can't see your screen.
You can see my screen.
Yes,
My screen is visible. Is that an issue from your hand? Try and check it again. I can see my screen.
okay.
Can you see it now? Can you see it now? I should restart. I should share the screen again.
Yes, I can see it now.
Okay, so let me take the explanation again. I said fractional crystallization. We stopped at simple crystallization last week, if you can remember. So today we are checking fractional crystallization. We said fractional crystallization is a separation technique that helps to separate mixtures that has two or more soluble solids. So anytime you see mixtures that has two or more soluble solids, so the things you need to pay attention to is this first part, two or more soluble solid that are based on difference in solubility. That is what fractional crystallization simply entails. And I was trying to refer to simple crystallization. I said this is a separation technique that helps to separate mixtures when we want to obtain one pure solid from another or from a solution. When we mix two substances together, but we want to obtain one pure solid. Let's say we want to obtain a pure copper sulfate from copper sulfate crystals. So what we simply do is we are using simple crystallization. Anytime you hear the word obtaining one pure or obtaining the purest form of a metal or of a solution, we use simple crystallization. It helps to obtain a pure solid from a solution. For example, copper 2 sulfate from its solution, we can obtain copper 2 sulfate from the entire crystals. So we can purify the copper that is being obtained. So that is what simple crystallization talks about. When you want to obtain one pure solid from its solution, when impurities are present in the entire solution. And fractional crystallization is just used to separate two or more soluble solid based on difference in solubility. And I gave you an example. I said separating a mixture of sodium chloride and potassium nitrate from a solution. The two of them are soluble, but one is more soluble than the other. So with that case, we can simply use fractional distillation since we have different insolubility level to obtain to separate the two mixtures. The 11th one, which is second to the last one, is magnetization. That is magnetic separation. Magnetization. Magnetization. So this is talking about magnetic. This is talking about magnetic separation. So anytime you see two or more magnetic substances in a solution, what you simply need to use for separating them is magnetization. That is, when you see two or more metals in a solution, like iron filings, aluminum filings, and all. So once you attach a a magnet to the substance, all the metals will join to the magnet. They will be attracted to the magnet you inserted into the solution, and everything that are not metal will still remain in the solution. So that is just how magnetization works. So magnetization is used to separate magnetic substances from non-magnetic ones by using a magnet. So that is just sorry. Sorry for that breakage. Sorry. Um, we were in magnetization, right? So I was saying it is used to separate magnetic substances. It is used to separate magnetic substance from non-magnetic ones. Using a magnet. So this is very straightforward. Let's assume that we have a beaker, for example. We have iron fillings. Let's name these iron fillings. All the circles, all the dots. Yeah. Let's name these iron fillings. And we have something like sulfur. Let's use dash 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 for sulfur. And all. And we want to separate this sulfur. S is the dash is sulfur, while the dot is the iron fillings. Iron fillings. So let's assume we want to separate this sulfur from iron. What we simply do is that we bring a magnet and we will introduce it to this solution here. So all the iron filings will be attached or attracted to the magnet here. So you see something like this, they'll be attracted to it. So by the time we put out the magnet, we'll have been sure that all the iron filings have been attracted to the magnet, thereby remaining only the sulfur in the container. So that is how we use magnetization. So there must be a magnet in the solution. If there is no magnet, we cannot use magnetization separation techniques to separate any substance. Until there's a magnet, we can use magnetization when there is one or more magnets in the solution. Then other non-magnetic substances too are there. So by the time we attach a magnet inside the solution, all the magnetic substances will be attracted to then the other remaining substances in the solution will be non-magnets. So the last one for separation techniques is decantation. I believe you understand what magnetization simply means. Is it? I need a response. Okay. So decantation. Decantation is the last one. This one we are very used to it. Decantation is just a process whereby we can pour off a liquid from a solid, or we can pour a liquid from another immiscible liquid without disturbing the bottom layer. You must take note of that. I will explain before giving you the notes. Probably you have two immiscible liquid that form two layers. So decantation is not a very accurate separation procedure, actually. We are trying to pour the upper layer away from the second layer. So you are just trying to be very careful. As if, let me say, for example, probably you want to take Gary and you soak Gary inside the water and you notice that there are so many debts in the Gary. You will go out and pour the liquid. You want to pour it away. You want to take it away. So that is decantation. There must be a second layer that must not be disturbed during decantation. If the second layer is disturbed, you cannot call it a decantation process. So decantation process is just a separation technique that entails the pouring of a liquid from a solid. And sometimes you can pour a liquid from another immiscible liquid that created two layers. Like you will see that, okay, this one is at the top, this one is at the downward. So you can pour away the first part and leave the second part. So that is just what decantation explains. For example, now, if you can use decantation to separate oil from water, because oil and water, they are two immiscible liquids. So they will create two layers. So in that procedure, as you are pouring it, water will be the first one to be going out, going out, going out. But it is not a very accurate separation procedure. Or probably there is a mixture of water and sand, and you want to pour out clean water from a settled sand. Underline the word settled sand. So you can easily use decantation by pouring the water, the clear water that is at the upper layer. You pour it away from the settled sand. That is decantation. So let me just give you the notes so that you can quickly write it down. So that is the notes. I want us to move to chemical combination and the mode constant. So once you are done writing it, please simplify. So let me know once you are done writing it, please. Are you there? Jesse, can you hear me? Are you done writing it? Chapter 2. I believe you understand everything that we considered so far in the first chapter. The pure and impure substances, the element, compound, and mixtures, the separation techniques, and the likes. This is the first topic that JAMB will be asking question from. At least you'll be seeing 2 to 3 questions on this topic alone. You can check your past questions and get familiar with the question. We're able to treat about 10 questions in the last class so that we can understand how these questions is always asked and might be asked for your own preparation for the exam. So today we want to start another topic, which is chemical combination, and the mole concept. Chemical combination and the mole concept. Chemical combination and the mole concept. So the first thing I want you to understand here is that under this topic, we'll be talking basically on the number of moles, mass, molar mass, number of particles, Avogadro's constant, and many things like that. These are the things we'll be talking on this part. So it is very important. It is just like a branch of quantitative chemistry. These topics help us to measure substances, to quantify, to know how quality a substance is and the quantity of such substances. That is what quantitative chemistry talks about. And that is what we'll be checking now. So the first part that we'll be checking is the relation between the number of mole the mass, the molar mass. Let me give you a sketch. I want to talk about number of moles, we talk about, which is M. It talks about mass, which is M. We talk about molar mass, which is M half. So the relationship between these three, you need to understand it so that you can understand how to use it to answer different kinds of questions under chemical combination and the mode concept. The relationship between these three things is N equals M over M half. So I believe you understand what this N is. N is the number of moles. M equals mass, and the MR is the molar mass. Anytime you are being given a question that contains the number of moles, the mass, and the molar mass, the first thing that should come to your mind is using this formula. This formula constituted these three parameters together. And there's a way you can easily find one thing or the other. In case they ask you to find the mass, the whole thing you do here is to cross multiply, isn't it? If you cross multiply, you can get your mass from this and simply say mass is equal to number of mole multiplied by relative formula mass, which is a molar mass. That is another. In case they ask you to find your mass, so this is the first. This is another formula that has been derived in case they ask you to find your mass. And in case they ask you to find the molar mass, you also make the molar mass the subject of the formula by simply saying molar mass is equal to mass over number of mole, isn't it? So that is how you apply this formula. Anytime you see number of mole, mass, and molar mass, I will still be giving you different examples and questions on this, but let me just explain it furthermore. And in case you see a question that talks about the number of particles, this is the case 2. The first one we check is case 1. So case 1 talks about the relationship between number of mole, mass, and molar mass. That is the case 1. Anytime you see a question talking about number of mole, mass, and molar mass, you use this formula that we just checked. But anytime you see a question talking about number of particles, number of moles, and Avogadro's number. So you won't use this first case, the first formula again. Since we are talking about number of particles, which is our capital letter N, and we have the number of moles, which is our small letter n, and we have Avogadro's number, which is n subscript a. What you simply do is you say your number of particles, which is your n, is equal to your number of moles multiplied by your Avogadro's number. I believe that is taken. That is the first. That is the first formula that we can have. That is the first formula that we can have. Sorry. So you can see the number of particles is equal to the number of moles multiplied by the Avogadro's number. So in case they ask us to find the number of moles, so what you simply do is that you make the number of moles the subject of the formula here. Use the number of moles as the subject of the formula. If you want to make the number of moles the subject of the formula, Eze, tell me how you are going to do that. What would be your n, your small letter n, in this kind of scenario? We want to make it the subject of the formula.
And small letter n will be equal to NA divided by B capital letter N.
NA divided by n. What do you say?
Yes, I said NA divided by N.
No, it is n divided by NA. Look at it, for example. This is the formula that we have before. N equals n multiplied by Na, right? Now we want to make N the rest of the formula. So we can divide both sides by Na. If we divide this side by Na, and we divide this by Na, this Na, we cancel this Na. Therefore, our N is equal to N divided by Na, not Na divided by N. Is that taking place? Is that taking?
Yes.
All right. So that is the second formula that we use under. I'm trying to give you how we get this formula. The case one is very simple. It talks about the relationship between number of moles, the mass, and the molar mass. The case two talks about the relationship between number of particles, the number of moles, and Avogadro's number. They'll be asking you a question on all these things. So once you remember the formula, you can actually apply them. So if you want to make Avogadro's number the root of the formula here, what would be the answer? You want to make Avogadro's number the root of the formula.
How are you, sir? That would be anything will be equal to capital letter N divided by small letter n.
Easy, please, give me 2 minutes. I'm trying to attend to something very urgent. Just 20 minutes. Okay, Na equals Avogadro's N over N. Yeah, you're right. Thank you. Just give me 2 minutes, please. Thank you. Okay, so let's continue the class. So I believe you understand how you can derive and make anything subject of a formula now. Sorry, I had a visitor I was not expecting, so that was why I quickly paused the class for a while. So let's just continue a little bit. So I will still give you some questions to deal with. But the first one, I believe you understand this formula already and you understand how you can apply it already. The first thing I want to teach you under this is chemical combination, so that I can give you examples for everything together. Chemical combination. So when we talk about chemical combination, we talk about how substances combine with one another to form a compound, or how substances combine in a particular level of proportion to form a compound. So, for example, you want to understand how much oxygen reacts with hydrogen, how many moles of sodium chloride are formed in a reaction, how many particles are involved, how many particles are later formed. So, to answer all these, we use law and mole concept to answer it. So, this chemical combination also is a very important topic that you need to pay attention to, because they'll be asking you a lot of questions on how substances combine, in what proportion were substances combining in order to form a compound, and so on and so forth. So you can just write it down. Chemical combination deals with how substances combine and what proportions they combine to form a specific compound. Then I will quickly go to law of chemical combination. After that, we are going to end the class. We will consider jam pass questions next week. My gosh, so this is the definition. Chemical combination deals with how substances combine and in what proportions to form compounds. It deals with how substances combine and in what proportions to form compounds. Please quickly write that down. For example, if we react oxygen with hydrogen, for example, do you know it will give us water, right? So by chemical combination, we can actually dictate how much oxygen reacts with hydrogen, how much oxygen reacts. So I'll still be giving you different examples on this topic. How much oxygen reacts with hydrogen. That's the first thing that we use chemical combination to do. Another thing is we can detect how many moles of water in this kind of situation. You can detect how many moles of water. You can see how many moles of water is formed. We have two hydrogen, two H, combining with one oxygen to give two molecules of water, right? So definitely, by the chemical combination theory, we can simply say that 2 moles of water are formed from the reactions, the combination of hydrogen and oxygen. So it also tells us how many moles of water are formed. I believe you are getting it easy. So the first thing we checked was chemical combination deals with how substances combine. And it helps us to understand proportions, the rate of the proportions to which they are combining. And they can also help us state how much is so much of and relation to do is that and we can know how many particles are involved. How many particles? How many particles are involved? So these are the things, like a summary that we use chemical combination to check. So let's quickly go to laws of chemical combination. JAMB really love this. I mean, they love this. The laws of chemical combination. JAMB really love this a lot. The laws of chemical combination. The laws of chemical combination. So we have different laws of chemical combination. The first one I want us to check is a law of conservation of matter. The law of conservation of matter. The law of conservation of matter. So you should know by now that matter is neither created nor destroyed during a chemical reaction. I believe you should know that. So it simply means that the total mass of the reactant is equivalent to the total mass of the product. And that is what law of conservation of matter is saying. Matter is neither created nor destroyed during a chemical reaction. So the same mass of reactants should be equivalent or should be the same to the total mass of the product. Let's say, for example, the same example I gave you. Let's say we have 2 moles of hydrogen combining with 1 mole of oxygen to have 2 moles of water. Mass before reaction must be the same thing as mass after reaction. We have 2 moles, 4 moles of hydrogen. Here we have 4 moles of hydrogen. We have 2 atoms of oxygen. We have 2 also, 2 times 0 here for oxygen also. We can see 4 plus 2 is equal to 6. 4 plus 2 is equal to 6. Is that taken? That is what law of conservation of matter talks about. It actually explains. Sorry. I want to open. So it actually explains that matter is neither created nor destroyed. Let me just give you the notes so that you can jot down something. So matter is neither created nor destroyed during a chemical reaction. During a chemical reaction. So like I said, simply means the total mass of reactants is equal to the total mass of the product. The total mass of the reactants is equal to the total mass of the product. So that's the first law of chemical combination. We call it law of conservation of matter. I want you to write that down so we can go to the second law, which is the law of definite proportions. Law of definite proportions. Law of definite proportions. So what law of definite proportion is talking about is that every compound will always contain the same elements in the same mass ratio. It's a definite, like it's something that is constant. So a compound will always contain the same element in the same mass ratio. That is law of definite proportion. For example, if you look at water as a compound, water always contains hydrogen and oxygen. And it has this constant mass ratio, which is 1:8. You get it? So that is what law of definite proportion talks about. It talks about a constant, a consistent mass ratio of the same elements in a compound. Definite proportion.
Kindly wait while he rejoins, but I think his network has an issue.
So, you know what the network is like this today. All right. So I was talking about law of multiple proportions before we had a network issue. So I was saying that law of multiple proportion talks about how two elements can combine to form more than one compound. More than one compound. So there's some elements they have uh, different valency. So when they combine with another element, sometimes if X and Y are combining, sometimes you see them forming XY, sometimes they form X2Y, sometimes they form XY2, sometimes they form X2Y3, and all like that. But these mass, they are always in simple whole number ratios. It must be a simple whole number ratios. So that is what law of multiple proportion talk about. So this is the note. You can quickly write down the note before we move to the. Let me just give you an example. Let me give you a realistic example. If you remember when carbon reacts, if carbon react with oxygen or combine with oxygen, sometimes we can have carbon monoxide. Carbon monoxide is just like all these gases that comes from an exhaust pipe of automobiles. It is very, very dangerous to the lung because it can change the color of the blood. There's something we call deoxyhemoglobin. When the color of the blood has changed to another color, like brick red. So when carbon reacts with oxygen, we have carbon monoxide, and this same carbon and oxygen, they can give us CO2, which is carbon dioxide or carbon dioxide. Carbon dioxide is just a gas that we exhale out, or in plants, they take it in. You can see CO2 is different from CO, but the same carbon reacted with oxygen to form two different compounds. That is the law of multiple proportion. When two same elements combine together to form different compounds. The fourth one, sorry, is the Gay-Lussac's law of combining volumes. What this one simply talks about is that they react in simple Gay-Lussac's. Let me type it out for you. Gay-Lussac's law of combining volumes. So it talks that gases react in simple volume ratios at the same temperature and pressure. For example, the same hydrogen and water and oxygen combining together I've been using since one. We said two molecules of hydrogen combined with one volume of oxygen. This is one, right? To give two volumes of steam, of water. Here, you can see that gases react in a simple volume ratios at the same temperature and pressure. That is what Gay-Lussac law of combining volume actually talked about. The fifth one is Avogadro's law. That one is very common. Avogadro's law. Avogadro's law talks about equal volume of gases at the same temperature and pressure. They contain equal numbers of molecules. They contain the same number of molecules. So in fact, during our secondary school days, we always use all these things to sing and talk. So equal volumes of Avogadro states that there is equal volume of gases at the same temperature and pressure that contains the same numbers of molecules. That is what Avogadro's law talked about. So I believe you understand all these 5 laws of chemical combinations. It talks about the Gay-Lussac's law of combining ratio. It talks about the Avogadro's law. It talks about the law of multiple proportion. It talks about the law of definite proportions. And it talks about the law of conservation of matter. For emphasis purpose, we said matter is never created under the law of conservation of matter. That there is the same number of moles in the reactant, the same number of mass in the reactant must be the same as the same number of mass in the product. Talks about the law of definite proportions, the law of multiple proportions, Gay-Lussac's law, and it talks about Avogadro's law. So, let me just give you this last thing for today, because many people did not join. I don't want to go too far. So the next class we'll be able to go very far. So we'll be talking about relative atomic mass in the next class. relative atomic mass. Relative atomic mass. Then we'll be able to solve some examples on the number of moles, the molar mass, the number of particles, the mass, the Avogadro's constant formula that I gave you the other time. So the number of the relative atomic mass is actually based on carbon atoms. So the have here is based on, I will explain this better in the next class, on the 12 carbon, which is 12. So what relative atomic mass talks about that is said it is the average mass of an atom when we compare it with 1 of 12 of carbon atom. So for example, argon, if we combine the relative atomic mass of oxygen, the AR is of O is 16. For sodium, it is 23, and Hall. So we just talked about the relative atomic mass is the average mass of an atom compared with 1/12 of carbon 12. 1/12 of carbon 12. So from here, we check the mole concept. Like I said, we began to check questions, and you must be able to memorize all the key formulas that I gave to you the other time. Now I told you that mole is the amount of substance that contains 6.02 × 10⁻23 particles, and this particles number is what we refer to as Avogadro's constant. So that is what moles explain, is the amount of substance that contains 6.02 × 10⁻23 particles of Avogadro's constant. Let me give you this example. I want you to do it. I will solve it in the next class. Calculate the number of moles is very simple, actually, but I don't want to end the class without giving you something to solve. So easy, do this. Calculate the number of moles in 22 grams of carbon 4 oxide. This is an example. So look at it. We have the mass. We can get the formula mass, the molar mass. Then we have a formula that linked, that joined the mass, the formula mass, and the number of moles together. So can you please quickly solve that? Or I should solve it for you. That was calculate the number of moles in 22 grams. Okay, I solve it for you. All right. So let me just solve this for you. They calculate the number of moles. So what they want us to calculate is the number of moles, question mark. They gave us mass to be 22 grams, isn't it? Let me erase this. Here's number of moles to be 22 grams. And if you remember that there's a formula I give to you the other time, number of moles equals mass over molar mass, if you still remember. So now they have to calculate this. We know this. How do we get our molar mass? Molar mass is we are adding CO2 together. Every molar mass of individual elements in the compound. For example, for the CO2, what is carbon? Carbon is 12. You need to go and know all these things. Oxygen is 16. That would be 16 times 2. So if we add it together, that would be 12 plus 32, which is equal to 44 grams per mole. 44 grams per mole. So since we know our MR to be 44 grams per mole, therefore, we can easily slot them to the formula which say number of mole equals mass over molar mass. So our number of mole is equal to, what is our mass now? 22 over 44. Then you find your answer. I believe that is clear. So we still consider many examples and we check many past questions in our next class. I want us to end it here because of others that couldn't join. I don't want us to go too deep and too far. Is that taken? So we'll be ending the class now. By God's grace, we will solve many questions as possible in the second chapter. Then we will check past questions on JAM on this topic also. So do well to enjoy the rest of your day. Is it?